with this particular chapter, what we focused last chapter on gases. We are going to take a look at liquids and solids. You'll find that there's far less math involved, so that's good for a lot of you, I think. However, there's still plenty of information there, kind of a little abstract, but we'll get through it. A lot of it you already know. About the first 12 or 13 slides, I'm going to pretty much skip over, go through very quickly, and summarize, because they are things that you already know, and I'll show you what I mean. Okay. What we're focusing on here is not chemical reactions. We're not focusing on the making of chemical molecules and the bonds that go into the formation of chemical molecules. What we're looking at and focusing on in this chapter is, if I have, say, a container full of carbon dioxide, how does each carbon dioxide interact with each other? They don't chemically react, right? But they can bump into each other. They can exert forces on each other that doesn't necessarily cause a shifting or a rearrangement of the atoms. Another way to look at this is, when I have a container of water, why does water stay together? Why do I have liquid water? Even when I pour it out, why doesn't it all just instantly disappear? Why does it stay together and form this predictable volume and mass of water until it evaporates? And that's what this chapter is about. It's about what's called intermolecular forces. We're going to talk about that. Forces that exist between molecules. Okay. Now, that's what this is. We'll see a lot of examples of this when you learn, like in your A&P classes. When you learn about how taste works, your taste buds, and your olfactory bulbs, how you smell things, realize that those are reactions that involve chemicals, but they are not necessarily what we would define as chemical reactions. They are not where two reactants come together and produce a product. Instead, what sometimes happens is a chemical will float around, land on the surface of, like, your taste bud, and there will be an exchange of forces that causes something to happen, not necessarily a conversion of a chemical into something else. Okay. All right, but to summarize these first several slides, I'm just going to go through about 12 slides here in a very short summary, so pay attention here. You tell me, what is the difference between solids, liquids, and gases? Somebody tell me the difference between those three things. If I have solid iron, liquid iron, and gaseous iron, what is the fundamental difference between those things? Okay, that's a good way to look at it. Density. You'll find that there's one particular case where that's not true, and I'll show you at the end of this lecture, probably tomorrow. But for the most part, density, right? Meaning how close together the molecules are, right, in the sample. The closer together they are, generally we say that's solid form, and as they spread out, they become a liquid, and even more farther apart, they become a gas. Okay, good. So realize what this implies, this chart right here. We know that solids have a definable shape that doesn't change, a fixed volume, a fixed shape, right? Not compressible. Liquids have a fixed volume, but not necessarily a fixed shape, right? Think of water in your graduated cylinder. When you pour in 10 mils, once you have 10 mils, you can pour it out on the table, and it now has a different shape, but it's still that 10 mils, right? So it's got a definite volume, although not a definite shape. Liquids are also not compressible. We don't really compress liquids. Gases, however, indefinite volume, indefinite shape. That's what all those equations were for last chapter. Are they compressible? Absolutely, because there's a lot of space between them. So we got some fundamental differences we got to keep in our mind here as we go along through this. So obviously, depending on how much space there is between the molecules, that's going to determine how much force of attraction exists between molecules. The closer together they are, the more they're probably going to exert an effect on each other, right? The farther apart they are, the less likely they are to bump into each other, and the less likely they are to affect one another. So that's all this is saying. Okay, things are closer together in a solid typically, and thus a solid form is going to behave a little differently than a gaseous form of something. Okay, we know gases are low density. We know they're fluid. They can move past each other. We know they take the shape of their container. We know they expand. We know they compress. Skip that slide. You know this about liquids, more dense than gases, also fluids, also take the shape of their container. Constant volume, not compressed. Solids, high density compared to the other ones, right? Non-fluid, doesn't flow past. The molecules that make up a solid don't flow past each other. They fix them. They vibrate, and they are moving. Don't think that they're not moving, but they're not freely flowing around each other like in a liquid or a gas. They don't change their shape, pretty much. Don't expand. They keep their own volume. Don't compress. In case you didn't get that so far, here's a picture, okay, to show you the compressibility and the non-compressibility of these things. Of course, the reason has to do with all the space between. We can minimize the space in gases. These, we cannot. Okay. One thing about, remember what we talked about with kinetic molecular theory with gases? Things are flying all around. There's lots of space between the gas molecules. They're bumping off their container walls, all that kind of stuff. Already talked about this. We can compress them, yada, yada, yada. Again, this is liquid. You already know this. Closer together, not compressible though. One thing I want to point out here is that if you have a container with a gas inside and you pop the lid, it has got a lot of energy in these molecules. They're high energy molecules. Okay? They can spread around. They're going to be bumping around, and they can find their way out the top of this container. Right? If it's a bottle of perfume and I open the lid, there's a reason you smell it. It's because it's in gaseous form. They're diffusing out, and they're spreading out and taking up more space. Eventually, they find a way into your nasal passages, and you can smell them. But in a liquid, they are also flowing and moving around, but not with as much energy as in a gas, so they don't have enough energy necessarily to escape the surface of this and leave. Some of them do. That's evaporation, right? On average, some of them, anytime you have a liquid, some of your molecules will be leaving the surface. That's evaporation. Now, we can affect evaporation. What can we do to increase the evaporation of something? Heat it up, okay? Someone else, I don't know, what did you say? That's good too. Both of those. We can use both of those. We can spread it out. That'll make it evaporate faster. We can add more heat. That'll make it evaporate faster. Good. Okay. Already said all this. I'm going to skip this. Now, this is where I'm going to start slowing down. Okay. We know the basic difference between solids, liquids, and gases. I'm on slide 13 now. Okay. You should look for this picture. We have two types of solids that we're going to discuss. Something called crystalline, something called amorphous. The prefix A means without, right? It means without. Morph means what? What do you think? Some people think change, but it actually, you'll see why people think that. It actually means something different. Shape. It means shape. So when you think of like Mighty Morphin Power Rangers, it's actually, and amorphous and things like that are changing. What that's in reference to is a changing of shape, not necessarily with them, I guess. They just put on a costume. But the whole point is to change shape. Okay, amorphous means without shape. Crystalline means it's sort of like what you think of as a crystal, something that's very geometrically organized and very, very highly organized in its shape. All right, so we're going to break them down into these two, one of these two, crystalline or amorphous. Things like salt and diamonds that are very, very geometric and organized, we call crystalline solids. Things like rubber, plastic, things that if you look at them, you just see sort of like the molecules all blobbed around each other, not really highly crystallized and organized. We call that amorphous solids. Okay? All right, we'll be dealing mostly with this kind of stuff, but realize that this certainly exists down here. Glass is a good example of an amorphous solid. I don't know if anyone has like a really old house that they live in. One of the first houses that my wife and I bought was built like back in the 1890s, and we remodeled it and stuff. But you look at some of those older windows that are in the original house. They're actually much thicker at the bottom, and when you look at it, you see it kind of wavy as you look through the glass. Glass is actually amorphous. It's mostly like a silica. It's made of sand and silica with some other particles in there. And older glass pouring techniques, we didn't have a lot of the stuff and the additives that we use now to balance all that out and smooth that the light refraction out. So what would happen is in the older ways, when they set it up, this was actually an amorphous solid. Glass is when it crystallizes, and it doesn't really crystallize. When it solidifies, it's not like a nice crystal that you can just look right through. It actually is amorphous, so it light will pass through and kind of get bent in all different directions. And as time goes on, these older glass, when these older windows are poured, things start to settle because they're not held together really well in such a repeating pattern. you can actually get settling of some of the molecules, and it gets a little thicker at the bottom of the glass. And all of that movement also creates some of the waviness that you see as you look through the glass. But anymore, of course, they've developed and engineered better techniques. Everything looks more clear when you look at it. You want to notice that block right there? See how that's sticking out? Does that bug anybody else but me? Figures. Just like that one right there. It's just like it stares at me. All right. There's one in the hallway out there, too. Just see if you notice it. Yeah, okay. I'll give you a bonus point if you can find it. I'll give you more than one. I'll give you 3 bonus points if you can find it. That's 3 bonus points, right? I mean, that's 3 points on a homework assignment. So, whoever gives it to me first, though, I only give it 1. Not everybody. You can't leave class to go find it either. Okay. So here begs the question is, why my daughter's in that stage, right? Why? But why? But why? Why is sugar a solid, but water's a liquid? Why? There actually is an answer, sort of. We can look at it from a chemical perspective and say it's because of what's happening between the molecules. Water, when it's a neighbor to another water, behaves a little bit differently than when I have a sugar next to another sugar. You will find that there are forces of attraction. There are not chemical bonds, but there are forces of attraction that draw certain molecules together more than others. And the stronger those are, obviously the harder they are to break. And things become different. The stronger they are, the more things you get like liquids and solids, right? And the weaker they are, the more likely you are to get a gas because the molecules are separated out from one another. So when you take a look at stuff like this, there's a lot of stuff to consider, a lot of stuff to look at here. Whether or not they can overcome the attraction, that depends on the state that they're in, like I just said. Okay, we'll determine their state, sorry. If they cannot overcome that attraction, then they lock together and they start forming like liquids and solids. If they can overcome it, they stay free and they stay in the gaseous state. Okay, now there's going to depend on a lot of things, and we're going to talk about this, but these things that draw like molecules together are going to be mostly dependent upon what's called electrostatic attraction. In other words, charges, positive and negativity. Now, if you take a CO2 molecule, for example, and you draw the Lewis structure, you will see that CO2, carbon dioxide, is a nonpolar molecule. Okay, we're going to come back to some of this stuff we've been learning. It's nonpolar. There's no positive, negative areas on there anywhere. It's not made by an ionic bond, so there's no cation and anion. Not only that, but there's no partial positive or partial negative region for polarity. So how do you get something positive, negative out of that? And I'll show you that in a little bit. Okay? But realize, anytime you have electrons, and we know now that electrons buzz around like crazy, right? They appear and reappear all over the place within these orbitals. Since you have moving electrons, you have electrostatic forces by definition, because they're going to be here sometimes, they're going to be somewhere else. And for a moment, an instant in time, you'll have a place where there's more and a place where there's less. Okay, and I'll explain all that here in a little bit. Polarity is going to come back. Okay, so Lewis structures determine whether or not something is polar, that kind of thing. I'm not going to make you go through the Lewis structure again as I'm lecturing, but realize that ties into what we're doing here. If you recognize polarity in a molecule, you can determine a lot about how it's going to behave, whether it's going to be a liquid or a solid or a gas, something like that. And I'll show you why. Okay, and then obviously whether or not they can overcome that attraction, like I said a minute ago, depends on the amount of kinetic energy they possess. Someone said heat it up. Well, by supplying heat, what you are making those molecules do is absorb more energy. The more energy that they have, the more likely they are to be able to break those attractive forces and keep away from them and spread themselves out. Okay, we've used this word before, right? When you use the word viscosity or something that's very viscous, you tend to think of it's really hard to pour, right? It's very thick and syrupy. And that's exactly what it is. It's resistance to flow in chemical terms. If it's hard to flow, we call it viscous. Obviously, the larger the attractive forces between the molecules, like if you look at syrup molecules and consider all the sugar and all the other stuff that's in there, there's a lot of attractive forces between the molecules. Not chemical reactions, not swapping of electrons, not changing atoms and making new products, just neighboring molecules next to each other. There's some kind of force that pulls them towards each other. And when that happens, whenever that's really strong, it's harder for them to move very freely, right? So the more those attractive forces are, the more viscous a liquid will be. Okay? So which, you consider which is more viscous. Something even like a Coke or gasoline. Coke isn't considered very viscous, but it certainly is more viscous than gasoline. Gasoline, the particles, the heptane and the octane that mostly comprises gasoline are very, very not attracted to one another. They stay separated very easily. Okay, so it's definitely not viscous at all. Okay, also consider molecular shape. When we start looking at molecular geometry and see how things are pointed, see where we do modeling like we did and see like little legs sticking out from molecules and all kinds of stuff like that, realize that they're not nice and round. It's like the difference between taking a pitcher full of marbles and pouring it, or a pitcher full of little jacks, like those little things you play with. Nobody plays with them really anymore, but you know what they are. When you try to pour those out, it's not going to flow very well, right? It's going to be a bunch of jagged edges that get caught on each other. Well, the same is true for molecules. The more the shape, the more complex their shape, the more resistant to flow there's going to be. Resistance to flow that there's going to be. Okay, now this is interesting. Something neat about liquids is a property known as surface tension. We know that if you take a cup of water, you can take a paper clip, right, or a lot of other things, and just set it gently on top of the water and make it float, right? Now, it is true that the density of that paper clip is actually the paper clip is more dense than the water. So the question is, why does it float? Because by all laws of nature, it should sink. I could take, even a piece of steel, right? I could spread it all out, and it would still float. Look at boats, for example. But I could wad it up into a smaller area, and it would sink. Okay, so what's going on here? It's more than just the density of the particular chemical involved, right? So what is surface tension in the case of water? Why would this paperclip float? What liquids have is they have this phenomenon that they exhibit where things at the surface, they like to really grab onto the molecules that are exposed to the surface and pull them in, create tension. That's why it's called surface tension. They tense up, they pull it in, and they try to minimize their surface area. For example, if I gave you a styrofoam cup, and I told you to fill it up as much as you can with water, and then very slowly, so as not to make any splashes, take a whole handful of pennies and start dropping them in, or sliding them in one at a time. You keep displacing the water, right? Keep pushing more and more water out of the way. What you will see after a while is a big dome of water forming on top of your cup. It will reach to the top, and where the cup ends, where you'd think it would overflow off the side, it won't. It'll actually bubble up and form like an upside down contact lens, right? Like a convex type of surface, a bubble, so to speak, a dome over the top of this cup. Now, it ain't going to go on forever, but it'll make a good one. Why is it doing this? It's because, and I'll show you a picture, but the water molecules are exerting forces on one another. One way you can break this, you can actually break surface tension, is by using soap. It's part of the reason that we use soap. Because if you take this cup and you put a tiny little bit of dish soap on your finger and touch that little dome at the top of the cup, it all comes rolling over the sides of the cup. Okay? You'll break that surface tension. Because soap actually works in a couple different ways, one of which is to take the forces that are between water molecules that are drawing them together and eliminate them. Break them, so to speak, so that the water molecules are forced to spread out from one another. So in essence, one thing that soap does is it makes water wetter. It spreads out water over a surface more than what it normally would be able to spread. Because normally, if you think of it, there's always like that, if you have a cup and you're not using soap and you rinse it out with water, you shake it out, but you look inside, there's always like a drop that's stuck in there. It doesn't just pour out. It stays stuck together. Water likes to stick to itself very much. It doesn't like to separate out very well. With a little bit of soap, you break that up, it pours out. Of course, then you got to keep rinsing out the soap. It's kind of a defeating process. But soap breaks surface tension. Now, it also does something else, which we're not going to get into here. I can mention a little bit later, but that's one thing that it does. Okay. Interestingly, if you have kids, there's some fun stuff you can do with this. You can, next time you're giving your kids a bath, let them make their own little boat. Take some aluminum foil, for example. Don't put any soap in the bathtub. Just fill it up with water. Let them sit in there and make a little boat out of tin foil or aluminum foil. And set it down, make sure it's going to float, and then take some dish soap or bubble bath, whatever it is you want to use. Put it on your finger and put it right on the back of that boat. Set it in the water. What do you think happens? It explodes. No. What do you think it does? Think about what soap does. What does soap do to water? Well, it's touching the rear of the boat, and then you set that boat in the water. So yes, the soap is now touching the water. You're close. It's going to break the surface tension. The boat's not going to sink. Maybe, but doubtful. I mean, I see where you're going with that, but if you actually do it, you'll see that the other happens. The only way you could really do that is, you have to have strategically placed soap. I thought you were going to say it spins around in circles, but you could do that too. If you put the soap all the way on one end of the boat, if you put it on the back right end, for example, and set it down, it would just spin around in a circle. But if you put it right in the center and put it on the back, it'll actually go forward. It'll travel. And the reason is because you all had the right idea. You were right. It breaks the surface tension, and what happens is immediately in that area where the surface tension is broken, the water molecules spread out, right? So instantly when they start spreading out, there's resistant force on the back of the boat, right? So it starts spreading out, and it ends up pushing the water that's coming towards the boat as it's spreading out, pushes the boat along. It's like just like a propulsion system. If you're shooting out, this is basic physics. If you got rocket blasters and you're shooting out, stuff behind you, it's pushing you forward, right? Well, you're doing the same thing, except you're using the water, breaking its surface tension as a pushing mechanism behind your boat, so it's pushing backward and causing you to go forward. Kind of neat. But once you do that, realize that you've now broke the surface tension in that water, and you can't just add more soap and do it again. You'd have to drain all of that water, make sure there's no soap left, put in regular water again, and then put the soap on it again. Because once you do it once, you've broke the surface tension. There was another one. Oh, another one that's not quite as involved. It's a little easier to do. Take a cup full of water, sprinkle some pepper in it, right? Because pepper floats on water. And then you can do the same thing. Put a little drop of soap on your fingertip, and then stick it right in the center of that little puddle of pepper. What do you think is going to happen? Yeah, that's exactly right. You're going to, instantly when you touch that water, all the pepper is going to shoot away from your finger. It's all going to shoot away, and you're going to have this big ring of pepper and then nothing around your finger. Exactly right. So you can go home and tell them what you learned today. So yeah, that's what you'll remember. Nothing else, but from this chapter, that's what you'll remember. Okay, so what you get is sort of a picture like this. Now imagine this, okay? I'm talking about the surface tension or whatever. Imagine this sample of water, and these are water molecules, and realize that neighboring water molecules, they exert a force on each other. And if you're the guy down in here, like this guy, you've got it coming from all directions, right? No matter where you go, all around you is force pulling you and prodding you and that kind of stuff. However, if you're the guy at the surface, notice you don't have anything above you, right? So it's sort of like when we went back to chemical bonding, I said, if I pull a bowling ball this way and she pulls it that way, which way will it end up going? It's all about balancing out the forces, right? What you get here is more pulling force down and less balance up here pulling it the other way, like you have all down through here, right? So what this ends up being is anything at the surface gets more of a pull inward because it's unbalanced. There's nothing up here pulling it the other direction. That is why it forms that little bit of a dome, and there's a little extra pull to the things on the surface as opposed to the things that are on the inside. So you create this surface tension. Now this surface tension is something to be reckoned with, especially, depending on like the angle that you strike. Like, you guys ever watch any of those deep impact stories of survival, like on Discovery Health Channel or TLC or whatever they're on? I saw one guy who was a base jumper. So you know what those are? They strap on their parachutes and they'll go off these high places no matter where they're at and just jump off of them, bridges, mountains, cliffs, whatever. Well, they were out west somewhere. I don't know, it was like Iowa, Idaho or something. And there was this giant bridge with this ravine in it or whatever. He jumped off of it, and there was at least two guys. I don't know if there was anybody else or not. And one guy was videotaping, right? And they were acting like fools, and they jumped off. And the guy holding the camera was a little late on pulling his chute. And there was water down below. The surface tension of water is pretty strong. And depending on, when you're hitting at that high of a velocity, not giving the water molecules enough time to move out of the way, and they act like an impenetrable force almost, coming that way. Well, he landed butt first on this water. Now, he pulled his chute, okay, and so he decreased the resistance a little bit, or increased the resistance a little bit and slowed his fall, but still it was very, very dangerous. He would have died if he wouldn't have pulled his chute. But he hit butt first in the water and blew a hole in his rectum. I mean, it made for a bad day. But anyways, so this is definitely something not to be taken lightly, I mean, you can go home and take a cup and jump on a cup and smash it with your butt, I guess. It's not going to hurt you. But, I mean, realize if you're falling, 80 miles an hour towards a water supply, I'm not sure what to tell you. All right. Well, anyways, this brings up something interesting, too, though. We're in this picture right here is in space, and notice that that's probably, say, like a bottle of water that's just poured out in space. Whenever we don't have gravity to deal with, what we have is a situation where the water molecules pull equally in all directions. So this surface tension doesn't have a surface anymore. There is no such thing as a surface. It's all the way around, right? The only reason we have a surface here is because everything's getting pulled down here and we got gravity and all this kind of stuff. Out here, when it's just poured out and floating in empty space where there's no gravity, the surface is 3 dimensions. It's all the way around. There really is no surface. It's like the surface of the Earth. We're a sphere. Where is the surface? Which way's up? Which way's down? Well, you define it. It's all relative, right? So whenever you consider this happening all over the surface of this, it explains why the sphere is the perfect shape. It explains why when we look out in space we have these giant stars that are spherical, not cubical, not any other shape. You've got all of these massive amounts of liquid, hydrogen and helium that are fusing together to just, release massive amounts of energy and power out into the universe. And we see these as stars, but there is liquid there too that is exerting these forces. Not only that, we've got stuff coming in from surface tension of all these liquids, but we've also got a lot of radiant energy bouncing straight back out in all directions. Okay, so a sphere represents all directions simultaneously. All right, interesting stuff. So you can break the surface tension. If you take that paper clip and you poke it hard enough, obviously you can apply enough force to break that surface tension. And once you've exceeded the surface tension and pushed it down into this area, it'll sink. Okay, so this brings us to cohesion and adhesion. Cohesive forces and adhesive forces. You've seen these words before, I know, like as a coach, I used to cohesive. We work as a cohesive unit. The cohesion is when you have a force of attraction between like molecules, the same thing. Okay, that's what creates surface tension, for example. Water molecules attracted to other water molecules, that's a cohesive force. Adhesive forces, or adhesion, is forces of attraction between molecules, but they are different types of molecules. They're not the same kind. Think of Band-Aids. They're called adhesive strips, right? Because there's an attraction there. There's not a chemical bond, because otherwise you wouldn't be able to remove it and put it back on. It's an intermolecular force that draws whatever the molecules are of the glue to your actual skin. There's adhesive forces there holding that all together. That can be, with a good enough tug, you can overcome that and remove it, put it back the way it was without changing the chemical composition of anything. For those of you in MLT, capillary tubes or whatever, you take a little tiny tube-like straw, touch a drop of blood, sucks it right up, right? Why does this work? Because of both of these forces, actually. Number one, adhesive forces explains why you could take blood and all the molecules that are in blood, and there is a weak attractive force between all molecules, including between the blood and the capillary tube. So they're sort of drawn together because of all the electron movement. And I'll explain that in more detail here in a minute. But once they get there, okay, once they come into that tube, what you need to realize is that, blood is mostly water anyway, right? And water has a high cohesiveness with itself. It likes to stick together. So what you get is a drawing into the tube of adhesive forces. Blood and all the molecules in the water and that kind of stuff sort of is weakly attracted to the molecules that make up the tube. Once they start to go in, though, immediately following that is more water-based stuff, more blood, because like with surface tension, we know water likes to stick together, right? So then that comes in with it. And then now, whatever molecules are on the very top of that blood sample, there's still some glass tubing left, right? So right there, they're attracted a little bit higher, and then everything else follows. And then the ones at the top are attracted to a little bit higher up on the glass tube. Then because of cohesion, everything follows. That all happens in fractions of a second, so that when you touch the drop of blood, it just zooms right up. Okay? So there's a lot of stuff going on there. This is the same reason, for example, we have the meniscus in our graduated cylinder. I tell you to read from the dip, right, the bottom of the meniscus. If you can imagine looking at the graduated cylinder and then looking down the top of it instead of looking from the side, realize that what you have is like a contact lens, right, at the top of your water, because everywhere the water is touching the glass, you've got a little bit of adhesion, a little bit of intermolecular attraction between the water and the glass that's in there. Now, all the ones in the center of the graduated cylinder, all those water molecules, they're not touching glass, right? They're not going to raise up. They're in the center. So that's why you have to read your volume according to that bottom of the dip, because those are where the center molecules are. Those are where the water molecules are that are in the center, not touching any glass. Because if you read it from the sides up, you're not really reading the volume. You're just looking at adhesion and seeing how those water molecules stick to the surface of the glass. Okay. Now, we know this to be true. We know that some molecules can escape the surface of a liquid, and we call that evaporation. When you have this whole entire sample like this, every one of these guys, if I look at this one, then I look at this one, and look at this one, they're all not going to possess the same amount of energy, just like us. We have an average energy that we can give to express the average of all of us, but in reality, we all have a little bit different amounts. The same is true with this. If at any given time, one of them could have enough to where it can separate out, overcome the intermolecular forces, and leave the surface as a gaseous molecule. That's what we call evaporation. So obviously, the more energy we put into this, the more this is going to happen, right? We're going to get more evaporation. We also call this vaporization. So evaporation and vaporization are the same thing. It's only a physical change, not a chemical change, because we still have the same thing that we started with. Okay? And we know, of course, we just call it vapor, the gaseous form of something. So if this is liquid water, this is water vapor. All right. This all happens at the surface, okay? Because that's the only place they can escape. We're not talking about anything on the interior of this liquid right now. Excuse me. That's what I just said here. Only ones with enough energy can escape. Okay. Amanda said a while ago that if we increase the surface area, we can increase the rate of evaporation. That's exactly right. And the reason is because evaporation happens at the surface, right? That's where these high energy molecules can escape. So it makes sense that if we give it more surface, we give it more routes of escaping. We spread it out so that more molecules are in contact with the surface at any given time, and thus more of them can escape. Obviously, temperature for reasons we've already discussed. Okay. Now, if the attractive forces between these molecules are very weak and they're not held together very well, like neighboring molecules, obviously they're going to be able to evaporate much more quickly. Think of gasoline and water. If I pour out 100 mils of gasoline and 100 mils of water, that gasoline is going to evaporate very, very quickly because the attractive forces between the gasoline molecules are very weak, whereas water is held together better. It's going to take longer for it to evaporate. So those that evaporate quickly we call volatile. The ones that don't evaporate quickly we call non-volatile. Now you have your sort of own slang terms for what you say volatile is. You think of a volatile situation, something that could blow up very easily. Well, carry that over into chemistry and realize that volatile means it evaporates very easily. And usually that's a bad thing because most of the time that means something in a gaseous form is very reactive and can combust very easily, and it usually does result in blowing up a lot of times, but not always. Okay. What does this mean? Just so we can learn to decipher words. The average kinetic energy is directly proportional to the Kelvin temperature. Put it in simpler terms. Anybody? Okay, when temperature goes up, as measured in Kelvin, which would be analogous to Celsius, right? The unit is, or the scale is the same in terms of the steps. As Kelvin temperature increases, so does energy. Makes sense. Easy enough. But like I said, not all the molecules in the sample are going to have the same energy. We're just talking about an average. Realize that's what a temperature is. When you take the temperature of something, what you are measuring is the average kinetic energy, the average energy of motion associated with the molecules that you have in your sample. It's an average. Okay. So that's why raising the temperature can increase those with enough, give some more of them enough energy to escape. Okay. Now, I want you to think about this, because we're going to start considering some things that are a little bit backwards than what you think they are. Notice what it says here. When you have something that's evaporating, okay, what you are in essence are allowing to happen is things that have a lot of energy associated with them, you are letting them leave. So when you are letting them leave, okay, since the higher energy molecules from the liquid are leaving, the total kinetic energy of the liquid decreases and the liquid cools. Okay? So it's not just about energy being radiated off into the environment. It's actually about losing high energy molecules. When you take a hot cup of coffee and you set it down and it cools, what is happening is at the surface, because this coffee is so hot, you've got a lot of high energy molecules that are actually escaping, going into a vapor form into the atmosphere. And carrying with them, they are taking a lot of the energy that was associated with this coffee, because they are the high energy molecules. They are storing a lot of that energy. So they're the ones that leave. And as they leave, things start to cool because they're the ones taking away that energy with them, leaving behind less energetic molecules. However, realize that the ones that are left behind start to redistribute their energy. So yes, the high ones leave, and then things start bumping around again, and before long, you've got some that are higher than others again. It never stays a perfect communist society. Okay? There's always the haves and the have-nots. So in this particular case, things get redistributed, and you're back to where you started. Now you've got some leaving the surface again. Okay? And that continues. And as long as there is liquid left, there will always be molecules that are able to absorb enough energy to leave the surface. That's why evaporation continues and continues, even when the high energy ones leave. Now you'll notice that at first, the hotter it is, the faster it'll evaporate. But if you leave that coffee out for a day, 2 days, a week, whatever, it will all eventually go away. As long as there is liquid left, you're going to continue evaporation, because whatever's left, whatever molecules are left, they're going to redistribute, start bumping around, and eventually some of them are going to gain enough energy again to just keep that process going until there are none left. Okay. Now, realize if I close a system, like I put a pot on top of the water that I'm boiling, or something like that, I can create what's called condensation, right? Condensation is whenever you have the vapor molecules that are produced bounce back and hit the surface of the liquid again and get trapped and brought back in. And you have a depositing again now of liquid that was once gas. Okay? That's condensation, sort of the formation of more liquid from the gaseous form. Okay. So notice what this says. If you have a trap situation, vapor molecules can bump around, stick to the surface of the container, start sticking to each other. Those little drops start forming on the side of the container, or they can bounce back in and hit the surface of the liquid. That's all condensing, coming back into its liquid form. Okay? Condensation. So another way to define it is when a gaseous form is converted into a liquid form, even if it's sporadic and sort of in different places at different times. Now, realize that evaporation, coming out, going into a gas, and condensation, gas going back into a liquid, are sort of equal but opposite processes. Okay? So if I have a system and it's closed, what you're going to see, for example, is we're going to achieve a state of dynamic equilibrium. I'll show you what I mean by that. Say this, if I have a sample of water molecules, it's sealed. I just poured it in, I sealed it. I got some space up here. What will start happening is very quickly we will start seeing evaporation, right? Because there's nothing up here. I've got some high energy molecules at the surface by default, and things are going to start evaporating. They're going to start accumulating. The more that starts to accumulate, the more they're going to start bumping into each other, the more they're going to bump into the walls, and the more it's going to start condensing back in, right? I'm still going to have some evaporation, but I'm going to start to get some condensation in the opposite direction. So you're going to have evaporation, 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 condensation, condensation, and they're going to meet sort of in the middle, okay? And that's what you're going to have. That's what I mean by dynamic equilibrium. Eventually, the condensation, the evaporation, they reach the same speed over a short amount of time. Now, everything is saturated with water vapor. That means it represents a point where that's the most water vapor it's going to have in that particular case. Now, it's dynamic equilibrium. That means everything's still moving. I still get a lot of evaporation, but I'm at the same time getting a lot of condensation to cancel it out. So everything is still moving. It's just when I step back and look at it, I don't see it changing anymore. Okay? That's dynamic equilibrium. Now, this takes us back to the last lab we did. Vapor pressure, right? We talked about when we collected gas over water, we had to account for the vapor pressure of all the oxygen that was produced in our little flask. And whatever water was there, we had to account for the vapor pressure of water so that we could just get the pressure of oxygen. Well, now we know a little bit more about this. Since evaporation always happens, whenever you get a vapor that's forming above the surface of a liquid, that's what we call the vapor pressure. It's exerting a force back down on the liquid. Okay, that's what we had to account for in our experiment. Okay, this is interesting because I don't think people realize this. So this is something you should walk out of here knowing. What boiling actually is. When you take a pot of water and you start boiling it, or if you take a mug or whatever, and you heat it up in the microwave and you pull it out and you see those little tiny bubbles start to form on the side, you know what I'm talking about? And sometimes they can sort of like feed into each other and start trickling and go pretty quick up the side. That isn't boiling. It's not water. Generally, what that is you've heated up the water so much as to any oxygen that was dissolved in the water, any nitrogen that was dissolved in the water because of the air or whatever, those get brought out. They're not dissolved anymore. They get converted into their gaseous state and they start escaping. When you actually have boiling, there's a difference between boiling and evaporation. Boiling is when you don't just have the molecules at the surface that are leaving in gaseous form. What you create in a situation of boiling is molecules that could be way down here in the bottom that turn into a gas right there, not at the surface. So they turn into a gas right here, and then they pop straight up, and they because they're less dense, they rise up. That's very different than evaporation, right? Because evaporation is only the things that are right here at the surface. Boiling could be anywhere down in here. They could turn into a gas at any point within this liquid. Now, when you think about boiling, take a look at what it actually is. When you see these bubbles start coming up from the bottom like this, they are empty space. There's actually nothing in them. It's kind of weird. You look at it, and it's a vacuum. It is nothing. Because it's this. If this was pure water, and you were boiling it, what those bubbles represent are empty pockets where water molecules have spread apart from each other. That's it. There's nothing in between them, as long as it's pure water, right? Little areas like this where there's more space than normal. And because of that, you create this little pseudo-boundary of water molecules that are far less dense than anything around them, so they start to float. They start to rise up to the top. So when you're looking at these bubbles, it's not like, it's not like a liquid bubble of water that we saw in space where there's stuff all along the inside forming that bubble. That was a liquid bubble. This right here, this gaseous bubble, is actually due to the fact that there's a bunch of empty space in there, and there's nothing there. So there's a difference between evaporation and boiling. Make sure you understand that. We supply enough energy to where even the molecules way down here can get converted straight into gaseous state and leave all the way from the bottom through the liquid out the top, not just the ones at the top. Okay. So everything has its own boiling point. And obviously the boiling point has to do with how strong its intermolecular forces are. The stronger these molecules are held together, the more energy it's going to take to boil them and turn them into a gas and spread them out. Okay. So it makes sense that the normal boiling point is the temperature. Basically, what you have to do is overcome atmospheric pressure. That's what you have to do. If you've got atmospheric pressure pushing down on you right here, you've got to give something enough energy to where the molecules can push past that pressure. And the temperature at which it is required to do that is the boiling point. So you can now see why the boiling point will change when you go way up high on a mountain. You tell me, the boiling point of water, will it be lower or higher on top of Mount Everest as opposed to here? Why? That's exactly right. You follow that? It doesn't require as much energy to push past and turn it into gaseous form. So you can have a much lower boiling point. Whereas if we went way down deep, some underwater city, that we had to use, we had 3 times atmospheric pressure, you're going to have a heck of a lot hotter temperature to boil water in that case than what you would even at atmospheric pressure here. Oh yeah, you're right. It's an average taken at sea level. Yeah. When we say something water freezes at 0 degrees Celsius and it boils at 100 degrees Celsius, yeah, that's exactly 1 atm at sea level. And most of the time, that's never actually the conditions that exist in it. So go in lab, and if you ever pay attention to the stuff we do in lab, take a measurement when you're boiling water. Sometimes you'll find it 98 degrees. You'll find it 99 degrees. It's never going to actually be 100. That's just a theoretical point that was measured to have a reference point. And also, we can get into, in a later chapter, since you're talking about chefs and cooking, there's tricks that you can do. Well, I'm going to explain here in a second about why you can never have liquid water hotter than a certain temperature. But some people, like if you cook spaghetti and pasta, put salt in there, some other things, and you can manipulate the temperature, and I'll explain all of that as to how that works. Why we throw salt on the road in the wintertime. I don't know if you ever think about that. You just get behind the salt truck, you go through your life and think, oh yeah, they're not salting the roads. You ever think about the chemistry of that? Why? Why throw salt on the road? Why not pepper? Why? Why not? Why does sand not melt the ice? It just gives you traction, but yet salt does. See, these are questions that you need to be able to answer. You need to be an informed citizen. Okay. Here's something interesting that you probably don't realize either. When you heat something up to boil it, you put it on your stove and you crank up the temperature. Some people get really impatient, right? They think, if I'm going to boil water, crap on this, heat it at 5 and let it warm up. Let's just torch this thing and let's get it going. Well, realize this. When you crank up the temperature, will you achieve the boiling point faster? Yes, probably. You'll probably get to boiling faster because you get your molecules more excited more quickly. However, realize that once you hit boiling, it is a waste of your time and money to leave your stove on high. You might as well just turn it down to 1 once you hit boiling. So that's sort of true. Because what happens is once molecules hit, notice here, heat added, temperature, we're climbing, we hit 100 degrees. We're boiling. Once water starts to boil, it will not get any hotter than 100 degrees Celsius, no matter what you do to its temperature. What you do to its heat source. You can crank it up. You can make it 3 times as hot as what it was before. You will not get liquid water hotter than 100 degrees Celsius. And the reason is because all of the energy that is absorbed by those molecules go into separating themselves. They go into weakening those intermolecular forces. So all that you're going to do is make it all boil away faster. As long as there is water left in your pot, and there is the process is happening where you are converting liquid water to gaseous water, as long as that is possible and still occurring, you cannot achieve a temperature higher than 100 degrees Celsius. Any extra energy, like I said, that you put in just gets shared between all the liquid water molecules that are left, and then more of them turn into a gas faster, okay, but not hotter. Does that make sense? You see what I mean? Now, what it will do is boil it away faster, but usually you're not trying to boil something away, right? Usually you're trying to use boiling water to cook something. That's why I say it's a waste of time, because if you were trying to boil something away, then yeah, crank it up, because your temperature is not going to change in your water, but your speed of boiling will. It'll convert more liquid to a gaseous form much more quickly. However, like I said, that's generally not what you're trying to do when you're in this situation. You're just trying to use that heat of boiling water to cook something. So turn it down, let it boil. That's it. Okay. Now, however, once you have converted all of that liquid to a steam, to a water vapor, then you will see that your temperature can shoot up. Because now you have these high energy gaseous molecules that are limitless. They can absorb a ton more energy. You can keep cranking up the temperature, and you will have an effect on them. You can make it very, very hot. But realize that at boiling, as long as it's bubbling, as long as it's boiling, you can't change the temperature. Now, I say that with a qualification. That's assuming normal conditions. You can manipulate this to your advantage, however. This is how pressure cookers work. This is how autoclaves work. If you can put a lid on what it is you're cooking, put a lid on your boiling water, what you have in essence done is created a higher pressure situation. You have trapped the gas molecules that are trying to leave, and you have forced condensation to happen, to come back in, right? They bounce off the lid, they come back and they hit in, they hit with each other. You force that back in. So what you are doing, think about it, you are trapping those high energy molecules that are trying to leave. You're trapping them and making them go back in, right? And we talked about pressure and boiling point a while ago. The more pressure that is pushing down on this, the more energy it's going to take to convert liquid water into gaseous water. So what that means is by putting the lid on and by creating, that's just a little bit of pressure, but if you seal it on, like in a pressure cooker or something like that, and let that pressure build inside of that, you are cramming down a lot of pressure inside that liquid and making it very, very difficult for those liquid molecules to get converted into gaseous molecules. So they absorb a lot more energy, and they try a lot harder, and it increases the temperature of the actual liquid, well past 100 degrees Celsius. Okay? So interesting stuff there. Okay, so think about this. Like I said a minute ago about evaporation, when it loses these high energy molecules, it starts to cool, right? This particular sample starts to cool. The liquid starts to cool. But as the liquid starts to cool, it starts to then absorb things from its surroundings. It's all about equilibrium, right? We have to, things aren't destroyed or created. If something goes out and it creates a difference, something's got to go in, right? So at first, there's a lot going out, and that's what cools it. But as it drastically loses a lot of energy, it actually, for a while, probably drops below even the energy that you have in room temperature. You ever notice that whenever you have a cup of coffee and you let it cool, it never cools past room temperature, does it? It never drops colder than what it is in the room. And there's a reason for that, because there's diffusion gradients that exist. As all of that energy is leaving that cup of coffee very quickly in those high-energy molecules, it starts to drop and get right to that point where sometimes it drops a little bit below the energy level in the room. And then you've got a situation where the energy in the room flows in, right? And then that continues. Stuff goes out, stuff goes in. It maintains a balance until where it all equals out to the room temperature. Okay? All right. So the liquid cools, but as the liquid, then the liquid, as it's cooling, it starts to absorb energy from the environment, right? To raise its temperature back to the same as the surroundings, like room temperature. Now, when heat starts flowing into a system like that cup, it starts absorbing heat from the environment like that. We call that an endothermic situation, endothermic process. Endo means into or within, right? Therm means heat, so putting heat into something. Okay, when heat flows out of the surroundings, it causes the surroundings to cool. Think about what I'm saying here. Okay, what I'm saying is, if you have a lot of evaporation at the surface, you have a lot of rapid cooling, right? By the mixture, not the environment. The mixture itself, the energy in it is cooling. want you to think about this for a minute because it's going to explain something that you do quite often. As this is leaving, high energy is leaving, this particular system starts pulling in some energy from the surroundings, right? Starts drawing it in to account for that which it just lost. That's balance. The surroundings now, not the system, but the surroundings are starting to feel the effects of losing energy that's going into that system to replace what that system lost, right? What that means is it actually starts to get cooler out here in the surroundings. Okay? This is cooling off as the system, or the coffee in this case, is cooling off. Realize to maintain a balance so that it doesn't shoot down too far, some of that energy has to come in from the surroundings. When energy starts to leave the surroundings and go into that system, out here in the surroundings it starts to get cooler because it's losing energy. That makes sense? So this explains why whenever you put alcohol on your skin, it feels cold. Okay? What happens is alcohol is a very volatile substance compared to like water. It evaporates very quickly. So when you rub it on, why it feels cold is because there's a lot of alcohol molecules exposed to the surface now that are evaporating very quickly. And as they are evaporating, like the situation I just said, when something goes out, something else has to start coming back in to fill that, right? A bunch of alcohol evaporates very quickly, and some of the energy then now must flow from the surroundings, i.e. your flesh, your skin. Some of the energy must flow from that into whatever alcohol is left until it's all done evaporating. So what in effect happens is it is drawing, in the process of its evaporation and trying to replenish all the energy that it's losing, it's drawing in heat energy from its environment, which is your skin in this case, and it feels cold. Okay? So you can explain that to your kids too, why it's cold when you put it on there. It doesn't matter if it's warm alcohol. It could be, sitting out underneath the kitchen sink. It's still going to be cold when you put it on there. Pretty crazy stuff. Now, the same is true now in reverse, though, except for condensation. In the case of condensation, you are taking those high energy molecules, and instead of letting them leave, you're bringing them back. So what do you think that does to that cup of coffee? If you trap that and bring those high energy molecules back, what do you think that does to its temperature? Evaporation cools it, right? Because it takes those high energy molecules and leaves it, takes it away. Condensation pulls them back in. So what does that do to it? It will increase the temperature. That's why when a can of soda pop sets out, it warms up, right? That condensation starts to form. The formation of condensation is actually taking higher energy gas molecules, forcing them into a liquid, trapping energy within that, and then radiating that out into the environment. Now, whenever you have this system that is now condensing, bringing in with it high energy, it has to breathe and it has to exhale some of that energy back out into the environment, right? When it does that, how do you think the environment feels? Warmer or colder? Warmer. The opposite of what we just did. Okay. Whenever you have heat that flows out into the environment, that's exothermic. Okay? Heat's flowing out. Exo. So this is one reason, for example, why a steam burn is so much worse than a regular hot water, scalding water burn. Because in the case of a steam burn, what you have are a bunch of tremendously high energy water molecules, right? They are in gaseous form, and they are very hot. They are a very high pressure situation. They've absorbed a ton of energy, more than what liquid water would ever absorb. And when that hits your skin, immediately it starts to condense. And those gaseous molecules start to come into a liquid form. And guess what happens? All of the high energy that was associated with gaseous molecules come together. And when they do, that traps in a whole lot of energy that has to be immediately dissipated and released. And guess where it gets released to? Your skin. That's why a steam burn is so much worse than a regular, just a scalding water burn. It condenses a whole lot more high energy molecules. Okay, now, the heat, what's called the heat of vaporization. Excuse me, the heat of vaporization is how much heat is required to vaporize something, to vaporize 1 mole of something. In other words, if I want to take water and take liquid water and turn it into a gas, how much energy do I need? We measure energy in joules and kilojoules, right? Also calories, when we talked about specific heat and all that. This is actually the only math that you're going to see. There's this and one other thing that's just like this that you'll see a little bit later. It's not that hard. If you see this, this is called heat of vaporization. How much energy it takes to vaporize something from a liquid to a gas. In the case of water, for example, it takes 40.7 kilojoules to vaporize 1 mole of water at its boiling point at 100 degrees Celsius. That's how much energy you would need. Notice the energy and temperature are different. This is obviously endothermic then, right? Because you have to put energy into it to make this happen. So obviously it's going to depend on the initial temperature, because if you're already at 99 degrees, you don't have to put very much energy in to get there, right? If you're at 0 degrees, you're at a much lower initial temperature. You got a lot farther to go, and that'll change. But I'm talking about this value is associated just with if you're at 100 degrees Celsius. How much energy would you need? Now realize that condensation and vaporization are equal but opposites, right? Vaporization, it's leaving, turning into a gas. Condensation, that gas is collected and brought back as a liquid. So it makes sense that mathematically they are the same value, they're just opposite directions, right? So that's what this means right here. The heat of vaporization is how much energy it takes to vaporize something, turn it into a gas. The heat of condensation is how much energy it takes to, how much energy must be pulled out to turn it from a gas back into a liquid. They should be the same value. Just you see the negative sign here, all that represents is different directions, coming in or going out. That's all that means. Okay. So if you take a look at some common liquids here, you'll notice, like for example, water, the boiling point's 100 degrees. Here's how much it takes, how much energy it takes at that boiling point to vaporize it. Here's some more common ones. Rubbing alcohol, you use that. Acetone or fingernail polish remover. Now it's non-acetone stuff, but the good stuff was acetone. For those of you in your cooking your meth labs, ether. Notice something about ether, though. Look at the normal boiling point of ether. Ether is extremely flammable, as you well know if you ever watch the news. Notice when it becomes volatile, when it becomes a gas, is at 34.5 degrees Celsius is its normal boiling point. 37 degrees Celsius is body temperature, right? So like 98. So you're looking like a nice, warm summer day. High 80s, probably 90, somewhere you could do the conversion. You're looking at boiling point of ether when you can't keep ether in liquid form anymore, and it's all vaporized. And you can see the dangers associated with that. Anyways, let me go through an example here. This is it. This is as complicated as the math gets, okay? So follow me on this. I want to know the amount of water in grams. So what does that mean? Grams means I'm going to have to find what first? Same in every problem we do in here. Moles. Okay. Calculate the amount of water in grams. In other words, first find moles and then convert to grams. That can be vaporized at its boiling point with 155 kilojoules of heat. So if I have that, what I do know is this. I know that the heat of vaporization for water, it says at its boiling point, right? So I know that I'm 100 degrees Celsius. I know that at 100 degrees Celsius, it takes this many kilojoules for every 1 mole that I have. Therefore, conversion factor. I know that that's equivalent to that. Okay? So what that means is I take my 150, this is a molar mass of water. I'm going to need that to convert it back to grams. Right? I'm going to take my 155 kilojoules that I know, use this conversion factor, and convert it to moles. Right? And once I have moles, I can use this to go to grams. And I'm done. That's the only math we'll have in this chapter. Okay, so kilojoules to moles, moles to grams. So this is how I do it. Here's my conversion factor. It's not given in the problem, but it was given in the table in the book. I'll give it to you on the test if you need to know it. The heat of vaporization will be given. It's not nothing you have to memorize. The heat of vaporization is 40.7 kilojoules per mole. What that means is this conversion factor is true. This or flipped, either way, however you need to use it. That'll get me to moles of water. How many moles? Now all I want is grams, so I convert my mole value to grams using the molar mass of water. And I get 68.626 sig figs, 68.6 grams of water. Okay? Easy enough? Now let me go ahead and take these last 5 minutes and try to get a little farther so I make sure we have enough time in lab. Okay, we talked about boiling. Let's talk about melting. Same stuff. We're just shifted up the graph a little bit. Notice it's the same thing, right? Last time we were up here. We were increasing the temperature to the boiling point where it leveled off, and then it went up again. We went down a little ways to a little bit colder to where we're increasing the temperature, and the same is true for melting. When you're trying to melt something, the temperature will not change until all of it is melted. And that's the thing, too, about, like, whenever you have your icing down coolers, icing down pop or whatever beverage of choice, you ice it all down, and you see a lot of ice water. And the water's really cold, and there's still some ice floating around. Now, realize that as long as there is some ice in the process of melting, your temperature is going to stay the same. It will not get any colder. You can bring in more ice, dump in a whole bag if you think it's getting low, fine, but you're wasting your time because that's not going to make it any colder than what it already is, right? For the same reason that we've already talked about. Whenever you do these energy changes, all that's going to happen is the molecules are going to share all this energy and push it around until that change of state has happened and everything is converted into a solid in this case. Or, sorry, into a liquid from the solid. They're going to keep focusing all the energy that you put into it or take away from it. So it makes, it just makes economic sense too. That you don't have to keep wasting a bunch of ice. But, all right. So the melting point then is the boiling point. Realize the boiling point is just a theoretical point between liquid and gas. You could be going from gas down to liquid. We call that the boiling point at which that change occurs. Or we could be going from liquid up to gas. Still, that teetering point where that happens is still called the boiling point. In the case of melting point, you could also call it the freezing point, right? It's the same thing. It's the point where you convert between solid and liquid. That's the melting point. Okay? It's called the melting point, but realize it's the exact same thing as what the freezing point would be if you're going from the other direction. Okay? All right. Now, when a solid melts, what is happening? Think about it. It's going from a solid to a liquid. Which has a higher energy state, liquid or solid? Which molecules possess more energy, if it's in a liquid form or a solid form? Compare solids, liquids, and gases. Liquid. So gases have the most energy associated with the molecules moving. Liquids have the next most. Solids have much less compared to the other two in terms of like kinetic energy and movement and all that kind of stuff. Okay? So when a solid melts, realize that for it to do that, it's got to take its molecules and put more energy into them, right, to go from a solid to a liquid. So it absorbs heat from its surroundings. Makes sense? Endothermic. Okay? Now, as heat flows out of the surroundings, it causes the surroundings to cool. Now think about this. This is why, and this is what people don't get, and I don't understand. I guess it's not that pressing, but I wish more people would sort of just understand how these things work. When you put ice in your drink, there is no such thing as coldness that radiates out and goes into your drink. When you take a piece of ice, you put it in your drink, it does not make your drink cold because the coldness from the ice is just leaving the ice. No. What is happening is that you're taking a solid that has a lower energy state, right? Ice, putting it into a liquid where the molecules have higher energy. So the energy is going to flow from the liquid into the solid, right? You watch that ice melt in your drink because it is absorbing kinetic energy from the molecules around it in your drink, right? So what happens is it pulls that energy out of your drink. There's no such thing as coldness, only the absence of heat. So it is pulling in the process of melting, turning in from a solid to a liquid ice, from liquid water, it's pulling in from the Coke that it's in the heat energy. So the Coke gets colder, right? Because it's losing energy to feed into that melting process. Does that make sense? You see what I mean? It's a little different than what most people think. That's actually what's happening. That's why your liquid cools whenever you put ice in it. Not because the coldness of the ice is radiating out. Opposite of that, it is sucking in all the energy from the environment, taking it away from the water molecules that are in your Coke, for example. Okay? Now, Think about this, though. We'll end on this slide. But when a liquid freezes, what has to happen? That means you're going from a liquid state to a solid state. So are you decreasing or increasing your energy? Huh? Decreasing. So what do you have to do with that energy? It has to go somewhere, right? You have to account for it. So when you freeze something, you don't put coldness into it. It's not what happens. When you freeze something, what you have to do is take energy from it, from its liquid form, and extract it and pull it out so that energy is not there anymore. And that leaves behind less energy that we call, a solid state now that's freezing. So that's why when you have a refrigerator or a freezer, there's that vent at the bottom that blows out that hot air, right? It's the way it works. It actually, the way that a refrigerator and a freezer work, it does not put in coldness. It does not, chill things and put in the cold temperature. What it does is it acts like a vacuum cleaner almost. Think of it like that. It sucks out all the warmth of everything that's in there. Any heat that's there, it extracts, collects in like a little freon. It gets absorbed in like a coolant, right? And it channels through, goes to a radiator, and then that heat is released out into the environment and blows out hot air underneath these appliances. Okay? So that's what it is. It's about extracting heat. It's not about putting in coldness. I hope that you can at least learn that from all of this. So in order to freeze something, you have to put heat out into the environment. You pull out heat from the system and put it in the surroundings. That's why it's exothermic. Okay? All right, we'll start there next time.